Hi everyone, my name is Emma and we're back again. Alright, so today we're going to make a super basic and easy volcano using materials that can commonly be found around the house, or they can be purchased for a couple bucks at your local grocery store. So for today, for our volcano, we will need some baking soda, some vinegar. Any type of vinegar will do. White vinegar, apple cider vinegar, etc., etc. Today, we'll be using apple cider vinegar because this is what I have around the house. And a clean plastic or glass bottle. Just pull this from the recycling, rinse it out with some soap and water, and we're good to go. And a paper towel. So the objective of today's experiment is to explore the properties of acids and bases, as today's volcano experiment will show an acid and base reaction. We'll create the appearance of a physical volcano eruption via a chemical reaction between our baking soda, aka our base, and our vinegar, aka our acid. So you may be wondering, what exactly is an acid and a base? Well, an acid is a solution that contains an excess of hydrogen atoms. Acids have a higher concentration of hydrogen ions than water. A base is a solution that has an excess of hydroxide ions. Bases have a lower concentration of hydrogen ions than pure water. So acids and bases are measured on a pH scale, which generally ranges from 0 to 14, but theoretically it can expand beyond 14. Now this is a logarithmic scale, and it's used to measure the acidity of a concentration of hydrogen ions in a solution. So the pH stands for potential hydrogen, since pH is effectively a measure of the concentration of hydrogen ions, that is protons, in a substance. How I mentioned previously, it's a logarithmic scale. So it's basically so that scientists can easily deal with large numbers. So each 1 unit change in pH corresponds to a 10-fold change in hydrogen ion concentration. So it's a lot easier to use this scale instead of always having to write down a bunch of zeros after your numbers. So once again, the pH is a negative logarithm of the hydrogen ion concentration. The square brackets, as you can see here, and around the H automatically mean concentration to that of a chemist. What the equation means is just what we've said previously. For each 1 unit change in pH, the hydrogen ion concentration changes tenfold. So the lower the concentration of hydrogen ions, the higher the pH will be. Acids range between 0 and 6 pH, with 0 being the most acidic. An acid is a sour-tasting compound that donates protons, or hydrogen ions, and/or accepts electrons. They contain more hydrogen ions than that of hydroxide ions. So some examples include citric acid that you can find in your oranges, gastric acid found in our stomachs, wine, and aspirin. On the other hand, bases have pH numbers above 7, as this indicates alkalinity, with 14 being the most basic. A base is a bitter-tasting compound that accepts protons and/or donates electrons. They contain more hydroxide ions than hydrogen ions. Examples include soaps, toothpaste, drain cleaners, and your typical batteries, like the alkaline batteries. So a pH of 7 is called neutral. This means that a pH of 7 is a solution that contains a concentration of hydrogen ions that is equal to that of pure water. Therefore, a 7 on the pH scale is pure water, which means that it's devoid of either acidity or alkalinity. This means that it contains equal numbers of both hydrogen ions and that of hydroxide ions. Therefore, it has a pH of 7, which is about halfway in between the scale of 0 and 14. Now you're probably thinking, how does this apply to real life? Well, pretty much everything around us can be identified as an acidic, alkaline, or basic, aka or neutral material. This includes, but it's not limited to, that of your blood, to that of your cleaning supplies, to what you're cooking, to that of coffee, to that of your saliva, and to a variety of other things. All right, so let's start the experiment, all right? Let's take our baking soda and tear off a piece of our paper towel. And we're just gonna pour a little bit of the baking soda into the paper towel and wrap it up. All right, so once we have that, see here, paper towel, some baking soda in it, we are going to take that and place it into our water bottle. Dropped it in. Okay. Now, we're going to get ready for our reaction to occur, and it's going to occur immediately after we add some of the vinegar to the water bottle that contains the paper towel with the baking soda inside. You see that and hear that? Can you hear that? So this is happening because our acidic vinegar is coming into contact with our alkaline baking soda. They're interacting together and having a chemical change as well as a physical change. This interaction amongst our acidic vinegar and our alkaline baking soda is making a reaction that we can see right here. And it's still going on. Hear it fizzing? So this reaction amongst our acid and our base is called neutralization. So when we had our acidic vinegar come into contact with our alkaline baking soda, they neutralize one another. Now our bottle is still emitting carbon dioxide, aka CO2. You can even hear it, which is what's creating those bubbles. We can still see those bubbles rising to the top, and we hear those popping noises. Now acids, such as our vinegar, which contains acetic acid, is what we use to get rid of the hydrogen ions. Because remember, acids want to get rid of their hydrogen ions. They did this by reacting with that of the base, aka our baking soda, which we used. So the reaction neutralized the acid and released carbon dioxide, which we saw via the bubbles, and it's still occurring, albeit a bit slower. And it produced carbon dioxide, aka CO2 gas. This gas wanted to escape from the liquid and was creating bubbles. Now these bubbles were building up and they created a foam, how we had initially seen. And they couldn't escape fast enough, nor pop fast enough. So they built up on top of one another, and that's the reason why we saw that foam initially. So once the acetic acid within our vinegar and the baking soda have neutralized one another, the reaction stops. As we've seen over the past couple of minutes, this reaction has gotten progressively less intense. Although we still see some bubbles here, they're not occurring at such a rapid rate, and there's no more foam. You also can't hear it anymore, see? Here. So basically, once our vinegar, which is our acid, and the baking soda, which is our base, have neutralized one another, the reaction has stopped. Meaning, no more carbon dioxide will be produced, as we are seeing, and therefore, no more carbon dioxide bubbles will be formed. As you can see, no more really being formed. It's slowing down the reaction. There's no more foam at the top, and you can't hear it. So once this reaction stops, our volcano is going to stop erupting. As we saw, it's no longer erupting. If you'd wish to start this all over again, you can always add some more baking soda to it and add a bit more vinegar to restart. Ooh. All over again. and we see it happening again and again. Well, thanks so much for coming today.